Hey guys, welcome to my garage where we're going to do some experiments to demonstrate different aspects of waves. So what we're going to do is we're going to use a slinky to demonstrate different components of a wave as it's moving down the length of the slinky. Just like the air can transmit sound waves, light waves can move through space, waves can move across the surface of the lake. Just like those things are transferring energy down them, so a slinky can transfer energy from one end of the slinky to the other in a wave. So what you're going to see and what we're going to do is make some measurements using these marks on this paper. So every one of these marks is 10 centimeters apart. Every fifth mark is bigger. Every 50 centimeters is bigger, just to make it a little easier for you to measure. So you're going to be measuring like the peak of the wave and the length it takes to reach the next peak. That will be the wavelength, for example. We'll also count how many waves go by in a given time. So we're going to make a bunch of measurements in this lab using the slinky as our demonstration. So if I stretch this out and I send just a single wave down the length of the slinky, you can see it bounces off of the wood at the end. It gets reflected back, huh? Now there's a couple things to notice. One, how tall is that wave? And the way we can measure that is with the tops of these marks. This is 10 centimeters right here, and this would be 20 centimeters from the center line. So we can actually measure if it's a smaller amplitude or a taller amplitude wave. Now what's particularly interesting about this single wave, watch what happens and specifically watch which side of the center line the wave moves down and which side it comes back on. Did you see that? So when I move the wave to the top of the page, the wave stays on that side, but when it bounced back, it came on the bottom of the page. So the reflection, in a way, was the reverse of the original. See that? Kind of like in a mirror. Came out backwards, huh? Okay, so now we're going to get into actually doing some experiments. And the first thing I want you to do is make a prediction about how fast the wave is traveling. I want you to make a comparison between a small wave and a large wave. A low amplitude versus a high amplitude wave. Which one do you think will move faster? So let me show you what I mean. I'm going to move my hand just a little bit for the first one, and I'm going to move it a lot for the second one. Which one will get back to my hand faster? So I'm going to have you start a timer. So you need a stopwatch. You can use your phone, would be great. I'm going to count down. I'm going to say 3, 2, 1, and then go. When I say go, I'll start the wave moving, and then you stop your timer when it hits my hand, when it bounces back to my hand. But first predict, which do you think is going to take longer? Which is going to be the faster wave? Will the low amplitude wave or the large amplitude wave be faster? Or of course you can always predict that they might be the same. So what do you think? Which is going to be faster? Small amplitude, which is the height of the wave, or large amplitude wave? Here we go with the small amplitude wave. Be ready with your stopwatch. 3, 2, 1, go. Now. When I said now is when I felt the wave hit my hand again. Let's take the average of 3 of those, okay? Small amplitude wave number 2, counting down. 3, 2, 1, go. Now, third one, counting down. 3, 2, 1, go. Now. Okay, so we're going to take the average of those 3 times. Take your stopwatch again, and I'm going to move the Slinky more. I'm going to put more energy into the Slinky. And let's see what happens when we compare their speeds. Here we go, the large amplitude wave, 3, 2, 1, go. Now. And again, 3, 2, 1, go. Now. When I say now is when it gets back to my hand. That's when you stop your stopwatch. Last one, 3, 2, 1, go. Now. Here we go with the small amplitude wave. Be ready with your stopwatch. 3, 2, 1, go. Now. When I said now is when I felt the wave hit my hand again. Let's take the average of 3 of those, okay? Small amplitude wave number 2, counting down. 3, 2, 1, go. Now. Third one, counting down. 3, 2, 1, go. Now. Okay, so we're going to take the average of those 3 times. Take your stopwatch again, and I'm going to move the Slinky more. I'm going to put more energy into the Slinky. And let's see what happens when we compare their speeds. Here we go, the large amplitude wave, 3, 2, 1, go. Now. And again, 3, 2, 1, go. Now. When I say now is when it gets back to my hand. That's when you stop your stopwatch. Last one, 3, 2, 1, go. Now. Now, one thing you might have noticed is how much the reflection continues. How many times does it bounce when I do the small amplitude wave versus the large amplitude wave? Here's the small. Watch how much it bounces. Here's the large. How many times did that bounce back and forth? Small wave, large wave. So which one had more energy in it? Which one had more power? In a way, I like thinking about it like power because this idea of amplitude is what we compare to volume when it comes to sound. The higher the wave, the bigger the difference between the top and the bottom, the louder the sound will be. It has more power. All right, now how did you do with your hypothesis? What happened in our results? What conclusions can you draw about the speed of the wave when it's small versus large amplitude? At the end of the previous segment, I mentioned sound waves, and I don't want to mislead you about them because I was not demonstrating a sound wave. There are 2 different kinds of waves. We call them longitudinal waves and transverse waves. Longitudinal means it goes the length of something, and that's what a sound wave does. Transverse waves go across something. And that's what the other type of wave I was demonstrating showed. That's the type of wave you see on the surface of the lake or that you have with light moving through space. So let's look at this sound wave and how it actually does move. So first of all, the previous waves were like this. Notice I'm moving the Slinky up and down. On the other hand, a sound wave is more like this. I move the Slinky forward and backward. And you can still see the wave bounce down there. It reflects off the end, just like an echo would bounce off of a cliff. But notice that the disturbance of the wave is moving in the same direction as the wave itself. The wave is going this way, and the disturbance is also going this way. That's why we call it a longitudinal wave. the disturbance moves along the length of the wave. On the other hand, with light waves and waves on water, transverse waves, they move perpendicular to the length of the wave. So the wave itself is going in this direction. We can see that. It's moving from my hand to the wood and then bounces back. But the disturbance is going up and down, a transverse wave going across the direction of the wave itself. So we're going to do some experiments with transverse waves, but remember that sound waves are a different type of wave. Longitudinal waves, going back and forth. And what we can see with the longitudinal waves is that we have a spot where the slinky is all compressed. We call that the zone of compression. The same thing happens with air molecules, with a sound. And then we have another spot where it's all stretched out, the zone of rarefaction. The molecules become more rare, I guess you could say. So this is what happens with sound waves. They get compressed and they get spread out in the zone of compression and the zone of rarefaction. And we can see that zone of compression moving down the length of the slinky and then echoing back to me. Okay, before we begin the lab itself, we need to define a couple of things, and I need to explain how to make some of the measurements. First of all, to review the two types of waves, we are going to study transverse waves in a moment. And remember, if it's transverse, it goes across. In other words, the wave itself is moving this direction, but the disturbance is perpendicular to that. It's doing this, back and forth here. The disturbance moves across the wave. And that would be for water. As you can see, it looks just like waves on water. Or it would also be for light. With sound, we have the other type of wave, the longitudinal wave. And in this case, the wave is moving this direction, but the disturbance is moving along the length of it. In other words, it's going long ways, you could say. And so the way we would draw that is by, for example, we often show sound waves something like this. Notice they're compressed together here, and then they spread out again. So it's squeezing and pulling instead of moving back and forth. Longitudinal versus transverse waves. Now we're going to do a lab where we're measuring some transverse waves with the slinky. And it's a little tough because it's moving quickly, so you have to look very carefully. And we have to come to some agreements about what we mean by a wave. So, here's point A, point B, point C. How long is one wave? A lot of people are going to say, oh, it's from A to B. But actually, what we're going to be measuring and what physicists measure is from one peak to another peak. This distance, that is one wave. From the peak of one wave to the peak of the next is a full cycle. Notice here it started up high, went down low. It's not done with the cycle yet until it returns to being up high again, right? You could also do this if we added point D. This would also be one wave. So you could choose to measure from the peak, also known as the crest of the wave, or you could choose to measure from one trough to another trough, the low point on the wave. Okay? But remember, if I'm counting waves, how many have I drawn here? I've drawn 2. Actually, I've just finished the second wave. From A to C is one wave. From A to E is a second wave. There's only 2 waves here. How about this one? How many waves would you count? 1, 2, 3, 4, 5, 6, 7, 8. Right? So that would be 8 waves. And when we're measuring the wavelength, again, it's from peak to peak. That is represented by the Greek letter lambda, from peak to peak. It should actually be identical to measuring from trough to trough. Okay? You can also see from these 2 waves that this one is a lot taller in this direction, isn't it, compared to this one. This is what we call amplitude. The height of the wave is the amplitude of the wave, how much movement there was, whereas this is the distance that it's moving. And so in our lab, you're going to be measuring this distance, the wavelength, lambda. You're going to measure that distance with some different demonstrations of the Slinky. You're also going to count how many waves have gone by. Remember, this is 1, 2, 3, 4, 5, 6, 7, 8. Oh, I guess it's actually 9 waves have gone by. Well, number 1, did that count as a wave? I think that's only half of a wave until it comes back down again, huh? But hopefully you get my point. You don't count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, don't do that. Do count 1, 2, 3, 4, 5, 6. Okay? So do count from peak to peak. If you need to pause the video at any time when I'm doing the demonstrations so that you can make this measurement, of course you're going to use these lines that I've drawn on the paper here. If you need to pause the video to make this measurement, do it. If you need to back the video up and start a stopwatch to count how many go by in 20 seconds, then do that. Do whatever it takes to gather the data, right? All right, let's do the lab. Okay, so now we're really going to do a lab. And we're going to make a comparison between 3 different conditions, and we're going to make 2 different kinds of measurements for each of those conditions. First, there's going to be slow waves. Second, medium waves. And third, fast waves. So I'm describing their frequency as slow, medium, or fast. And you're going to measure 2 things about them. First, you're going to measure the distance between the peak of one wave and the peak of the next. For the slow waves, for the medium waves, and for the fast waves. Peak to peak, which is the wavelength. So you're going to measure wavelength. Then you're going to need to pause the video, back it up, and you're going to count how many waves go by in 20 seconds. I'm not only going to send one wave by, I'm going to keep sending them, one after another, either slow, medium, or fast. So you're going to have to measure 2 things. To do that, you'll need to stop the video, back it up again, and count when you start a timer for 20 seconds. Count how many waves go by during that time. All right? So we will start with the slow waves. And I'm going to try to make sure that all the waves are about the same height, the same amplitude. In other words, how big the wave is. I'm going to aim for about 20 centimeter amplitudes. And we're going to do the slow wave first. So what you're supposed to do first of all is measure the height between one peak and the next. Excuse me, the distance along the length of the wave. Now this one's a little tricky because it looks to me like there's only one wave at a time on here. So we don't actually see more than one peak at a time. So we're going to have to figure that out. I would say, let's do this. Go to the top of the wave here, and then where does it hit the bottom over there? That's not actually the wavelength. That's just from one peak to one trough. So what you need to do next is double that. Just because this is a slower wave. It has a really long wavelength, so we can't see the whole thing here. So we have to go from peak to peak. To do that, we're going to have to go from peak to trough and double it. Then I want you to count how many waves, how many peaks you see in a 20-second period. So you'll have to back up your video, start a timer, and count the number of waves you see in 20 seconds. Those are what we call oscillations. Each wave is an oscillation. I think we've done more than 20 seconds now. Okay, so I'm going to stop that one. Now, I'm going to do the same thing again, and you're going to do the same thing again. I'm going to move it about the same amount, but I'm going to move it faster. I'm going to try to do this at a medium speed now. And you're going to measure the wavelength, and then you're going to count the number of waves in 20 seconds, the oscillations that occur. So here we go, medium speed. Now I think you might be able to see two peaks at once here. So make sure you're measuring from peak to peak. Again, you could measure from peak to crest. Excuse me, the crest is another name for the peak. It's the same thing. So either measure from peak to peak or from crest to crest. What we did on the previous one, because it was such a long wave, was it went from peak to trough, and then we doubled that to get the correct wavelength. But not this time. This time you just go from peak to peak. How many centimeters long is it? You have to use the marks on the paper to do that measurement. Once you've got that figured out, you can back up the video, and I want you to count how many waves go by in 20 seconds. You'll need to start a timer. Count the number of waves in 20 seconds to find the oscillations. If you need to pause the video at any time to make those measurements, that's what you should do. I think that's been enough time though, so I'm going to stop that one. The third one, you're going to do the same thing again. Measure the wavelength from peak to peak when I oscillate it quickly. So you need to count the number of oscillations in 20 seconds. You need to measure the distance using these lines when I have a high frequency, a fast frequency. So here we go, fast frequency. Pause it if you need to. Measure the distance from one peak to another. When you're counting these, you might just want to count how many times my hand moves. That will be your oscillations. But only count on one side. Like every time my hand gets to my right knee, count that one. Oh boy, this is killing me. I gotta stop. I hope that was 20 seconds. All right, let's analyze our data.